Hi, my name is Alec Lantain, and I'll be presenting to you the design of a drone light show production system. So what is a drone light show? A drone light show is a combination of several drones flying in unison, all while emitting different colored lights and flying in a variety of patterns in order to make a light show. So to better understand a drone light show, we need to understand the industry behind it. So in 2012, for the entertainment industry, there was a $520.24 billion profit, which represents about 29.2% of the global revenue. That's huge. And in 2017, that number is actually, by the end of it, it's projected to increase to about $655 billion, or about 29.4% of the global revenue. So this is a massive market, and we believe that adding a variety to it would attract more demand to the industry. So we need to also understand that there are different types of light shows and the context behind them as well. So we're focusing on fireworks and laser light shows. So for fireworks, in the year 2010, there was a consumer revenue of about $636 million, and that number actually increased to $755 million in 2015. Now, the trade-off here is that fireworks were the fourth largest injury in terms of annual injuries in the year 2015, and you can see that by the number of 12,000 injuries. Now, we do believe that there's potential to switch existing market customers from the current market with a better alternative. For our project, we specifically believe that projects outdoors become much more complicated due to a variety of hazards that come with nature. So storms, wind, and other unforeseen circumstances could hinder the safety of the project, and as a result, we're limiting our scope to the indoors. So for indoor stadiums, there's still a massive market, and as you can see, there's 327 total indoor stadiums. That still provides us a massive capacity for seats, and if we look at the NBA, for instance, there's about 30 teams in the NBA with about 82 home games per team, which gives us about 1,200 home games total. We'll go over this later, but that's a huge market to go into. So for the problem need statement, we understand that the revenue for entertainment industry is growing annually, and existing light shows are not improving, and they emit pollution, they're not progressive in technology, and they're not reusable. Due to this problem, there's a need for a new light show system that's entertaining, safe, and environmentally friendly. For the stakeholders, we have 5 main stakeholders, and then we have 6 indirect stakeholders, and basically these represent the interaction between both direct and indirect. It's also important to note that no stakeholders are blocking our show from happening, regardless of the tensions that are shown, and that's really big. So that allows us to be able to continue our project. Now onto the concept of operations. Preceding the show, the main focus will be the venue assessment for risks and other parameters to enable customization of the show, including preliminary testing and ensuring the venues meeting the legal requirements. So those are our first main 6 steps. And then the day of the show, operations will focus on the preparation of drones and the entire system to ensure the performance runs smoothly. This includes setting up the communication system and having all the outdoor requirements set as well. Our mission requirements were created primarily with safety in mind. We also had a variety of different requirements such as simulation requirements, the design requirements, and others to ensure that our system is fully functional and we meet all the standards that are needed to make this happen. So one of the most important aspects of our project was the simulation to ensure safety. So our simulations models were divided into 2 main sections, the lead follow control model and the risk model. Our lead model was developed to evaluate the relative trajectory of a lead-follow pair, and we used PID tuning in order to minimize any separation errors based on the target values. We also measured actual separation to ensure the correct relative positions along with the flight paths, and this gave us a variety of outputs. This is basically the chart that shows our control process. So as you can see, there's a lead input for the drones, which then leads us to the PID controller, and as an output we're given the follow drone, and this has a small delay, but the system constantly updates the target separation, and as a result the PID varies. So the lead follow transfer functions were derived in order to take into account any potential position error, delay, and disturbance for the system. The top box basically shows the final positions without disturbance, whereas the bottom includes disturbance. Our drone lead follow separation control system is divided into three main partitions. From top to bottom, you can see that there's three boxes. There's position X, Y, and Z. And then on the left side, there's another box which shows the lead drone. The green box in the middle shows the PID, and the box on the right shows the follow drone. As a result, we were given different scopes which provide different outputs to basically see any changes that we need to make for our system. And we use system verification by simulation for the PID controller itself to be able to test our model. And this was divided into the proportional, integral, and derivative controls, which in the yellow chart shows what we thought would happen when we change each. So for KP, there were several different values that we were able to assess, and the one highlighted in yellow shows the best KP value that we had. So the KP of 2.75 had a faster response and no disturbance, and you can see that primarily with this small increase right here. There is no delay, whereas KP of 1 has this immediate almost 10-second delay, where the system basically can do nothing. Now the bottom two values show disturbance in the step functions, as you can see right here. KI was similar to basically show the KI. We have two main charts, and you can see here as well that the distance, or I'm sorry, the disturbance is quite noticeable for a KI value of 0.5, whereas 0.05 immediately shoots up. Now this shows that there's a faster response, and that's why KI of 0.05 would be better. And once again for KD, we can see the same thing. So the smaller the value, the fastest it would reach steady state, and the error is also 0 for steady state error. Now, as a result, we're given two 3D plots, and these two 3D plots at the bottom show the same exact thing. They're just shown in different angles. So the red signifies the follow drone, and the blue signifies the lead drone. And onto the risk model. So the risk model is divided into two main sections. We first focus on the kinetic energy model, which focuses on the velocity and the surroundings of the drone itself. And basically we go into the fatality, injury, and property damage for drones. Then the second risk model calculates the near mid-air collisions and the mid-air collisions for the drones, which also focuses on the show but not the environment around it. And this also focuses on the drone velocities too. So this chart on the right basically shows the velocity to kinetic energy, and it's not specific to our system, but it is actually completely relevant. It's a study that's conducted by Monash University in 2013, and it shows us the acceptable velocity region. So basically we were able to use our drone to be able to, in our risk model, to evaluate the specific fatality, injury, and property damage risks associated. And we can see that with slide 30, which is the risk model that we created. So it basically uses the different inputs of the Aztec Hummingbird drone in order to see what outputs would happen and see if the specific joule level would be high enough for a fatality to happen, an injury to happen, or any damage to property to occur. And our output basically showed for the Aztec Hummingbird that about 15 meters per second would be the max velocity for an Aztec Hummingbird to create a fatal injury risk. Now, for the separation distance and near mid-air collisions, based on randomly created velocities, we were able to compute the different separation distances for two drones in order to calculate mid-air collisions. We then increased the risk model to include 11 drones and found that 13.7 bin distribution had a higher frequency. Our mean separation distance here was about 12.55. Then we lastly ran the risk model using 101 drones, and the mean separation distance remained around 13, which is very good. Lastly, we had the business case, and the business case was very important for our project because we're in the entertainment industry. Without the business case, we'd have nothing. The business case was divided into three main sections: the utility and decision analysis to pick a best drone, the budget, which is self-explanatory. It's calculating the startup costs, fixed costs, and variable costs. And lastly, we have the break-even location scenarios to basically show that our product has a broad market and anything is possible for different scenarios. So our utility was divided into three main partitions. We had the performance, safety, and capability of the drone, and these were all weighted equally and had several attributes associated with each. We were able to then get different ratings for each drone, and as you could see, the Intel Shooting Star had the highest rating of 7.9, and next was the Aztec Hummingbird with 7.066. Unfortunately, the the Intel Shooting Star is not available in the current market. It's only essentially a beta drone, so we wouldn't be able to use it. But the Aztec Hummingbird is still a great drone, and that's evident in the cost versus utility diagram. So the Intel Shooting Star is the highest, but the Aztec Hummingbird is a close second and is still a viable drone to use. Next, we have the total cost breakdown, which was divided into startup and recurring costs, and then recurring went into fixed and variable costs. So the startup costs were divided into construction costs and drone transportation, and basically ended up being about $500,000 for the Aztec Hummingbird. Next were the yearly recurring costs for fixed and variable prices, and that was shown in the black boxes or the black lines, and we divided this also into optimistic and pessimistic values because for maintenance you never know what can happen, which was about $90,000 for the Aztec Hummingbird. So that led us to our overall budget for 2 years. It would be about $1 million to $1.2 million, depending on how optimistic or pessimistic our values are. So we had two main scenarios to show how versatile our product is. We had Eagle Bank Arena, which had about a $40,000 fee, and then we had the Center for Performing Arts, which had about a $9,000 fee. And this is shown in our venue scenario costs, which showed that Scenario A was a larger venue and more expensive, but Scenario B was also much smaller. And we can see that in our break-even, that Eagle Bank Arena was $122 for one show to break even, but as soon as we hit 20 shows, it's only $14, which we think is a very valuable cost. Next is the Center for Performing Arts, which had a much higher cost because of a smaller capacity, but once we had 50 shows, it was only $23 a ticket. Lastly, we talked about the NBA, and we said that there are 1,200 games, so if we had 10% of those games, it would be about 123 games. If we only had one added dollar to the tickets sold at an NBA game, we would have a profit of $800,000 for our show, and we think that's massive. Thank you, and I hope you enjoyed our project.